a recording of this one on YouTube. All right, so this is actually a slide that I put in for the retrospective page after the SharkFest, so that everybody can follow along and download the traces if you want to. But you might as well also just quickly download the demo traces using one of those two links. The one is the short link, and in case you're a little bit paranoia, then you might also use the longer one. And I also put a few references to the commands and tools that I used during my labbing and my research. Right, so a few things about me. My name is Simon. I live and work in Germany for Miele, which is a household appliance manufacturer, basically. One or the other might have some of them at home. I'm in the position of a network engineer, basically, but I also do quite a lot of troubleshooting in-house concerning applications and everything that runs in our data centers. Yeah, and then as some sort of part-time job, I like to do troubleshooting for others if it's necessary, or if I can help them from remote. Yes. Yes. Sure. Password is SF18US, SharkFest 18US. Okay. Sure. Okay. Yeah, in my free time I do a couple of other things, but let us maybe just jump right into traces. And I brought a little first demo that I'm just going to open here. You might open it on yourself or just follow along on the screen, because all I want you to do is to take a look at it. Might need to make it a little bit bigger for you. And just tell me what you see, and if there is anything that makes you think, that's not what I expected to see here. So what do we see? It's a quite short trace, so we could basically start at the beginning. What do we see right at the beginning of the trace? Anybody? A handshake, yes. So with basically a three-way handshake, what port are we using, or what application are we using most likely? Yes, HTTP. So this is a connect to a web server. What else can you see? So there's a GET request, and followed by what? And then not found. So right. So we are seeing a 404 from the web server coming back to us, basically saying, hey, that file or that directory that you are requesting, in this case it's the TUF icon, I do not have this, I cannot find this. So following along, what is this part? Anybody?
Acknowledgement and termination of the connection.
Yes, so we have a termination of the connection, actually in the very most polite way. So what we see is a fin-ACK in both directions, so both agreed on closing the TCP connection in this case, right? So what happens now? We see a GET again. HTTP GET. Is this the same session? Can you tell from just looking at it, or do you need any more information?
The source port is different.
Correct, the source port is different. So we can assume that this is another connection, right? But shouldn't we see something else before we see a GET request? Mm-hmm. Usually we would expect to see something like right in the beginning. We should see a perfect three-way handshake, and then something that requires or that uses the application, in this case a GET request. So let's just maybe look into this GET And I will just open up the TCP header for you. What do you see there? It's right here on the screen. It's actually marked. There are options in there, that's correct. But what is this? Yeah. There's a SYN flag set in the HTTP GET request. Anybody seen that before? TFO. Yes, correct, TFO. Good spot. So TFO means TCP Fast Open. Anybody heard about that before? Raise your hand if anybody was seeing TCP Fast Open before. Okay, quite a lot. So let's see. We'll just switch back to the slides, and then I will show you how it looks like later on. Oh, sorry. Switch in.
I thought there wasn't supposed to be any data in syntax.
That's right. So the question was, I was not expecting any data in the SYN packet, and this is what the original RFC says, basically, right? So if you open up the TCP RFC 793, you would see that you are actually not allowed. So how does this work here right now? I think I need to quit the presentation and start it again. And there you go. It's basically not allowed to send any data in a SYN packet. And that's correct. But luckily, we are not in 1970s anymore, and we can do something about this. So once again, in a perfect traditional three-way handshake, we have something like this, right? You have seen this over and over again during the conference. And right after that, I can start and send data or request any data from that server I'm connecting to. But the drawback of this actually is that I lose one round-trip time before I can actually request anything from that server. And imagine the server could be far away, so we might have a 300 millisecond latency in there. And here's a nice statistic about page load times. So this is basically from a talk from a guy, from Mike Belchi. I put the reference down there. And what you can see is that page load times in milliseconds, which is right here, does not decrease significantly if you increase your bandwidth of your local internet access, for example. So maybe up on 5 megabits per second, you see a decrease of page load times, but after that, it doesn't matter anymore. So if you're not watching 4K YouTube videos, you should be fine with a 5 meg internet access at home, right? On the other hand, what we see is a linear correlation between latency and page load times. So the further away your server is you're connecting to, the slower is the actual page load. So what can we do? TCP Fast Open is a good way to approach this because we might save us one round-trip time before requesting data. So let's look at this in detail. TCP Fast Open is a fairly new RFC for TCP. If you imagine we are back in the 1970s for the original one. And what it basically addresses is exactly this, that we need to save some time during the connection initiation. So let's look at the client and server scenario again. In the TCP Fast Open first connection, so that is the first connection a particular client ever creates to a receiver or to a server, it will send a TCP SYN with the TCP Fast Open cookie request in that. So that is in the TCP options, you will find this. Upon receive of this SYN request, the server creates a cookie for this client based on his IP address and some sort of secret. So it basically hashes a few things to create a cookie. Then it's going to send back the SYN ACK, including a TCP Fast Open cookie to that client. And then to round this up, obviously the client sends an ACK back to the server. And here you can see basically how one of these cookies looks like. It's nothing fancy, it's not very long, 64 bits. But it will be unique for every client that connects to this server. So now the magic actually starts to happen with the second connection from that particular client to the same server. So with that, the client can send a SYN, including data, including the SYN cookie to that server. And then the server is actually allowed to send data within the SYN ACK back to the client. And what this basically means is that we are saving this one round trip for this maybe simple and small GET request that we want to see from the server, right? And then exactly what you mentioned earlier, the original RFC says, well, there must not be any data in the SYN packet, right? But this is kind of obsolete with the TCP Fast Open RFC. If the server doesn't support it, and we will see that on the next slide probably, it will just either drop the packet, which might be bad because then the client runs into the retransmission timeout before it can actually resend a SYN without a fast open request, or it just answers without a cookie, and then the client knows, okay, the server does not support fast open. Right.
Simon, in this slide you say that the SYN ACK can also take data in your trace. It doesn't.
That's correct. Yeah, this was a question in the slide, during the talk yesterday already. So Carrie asked in that recap that I was showing. I can just open it up again for you. What we see after that GET and SYN from the, sorry, you don't see anything. Let me duplicate my screen. So after that SYN and GET request from the client, we don't see any data coming back from the server in the SYN ACK. The length is 0, right? So why isn't there any data in that? And the answer to that is it depends on the implementation of TCP Fast Open on that server. In this particular example, I think it was the Ubuntu Linux server. So either the implementation is not quite right in this case, or if you send a GET request to a HTTP server, and the SYN ACK usually comes pretty fast back to the client, it doesn't have the answer yet, and that's why it's just sending the SYN ACK, the empty SYN ACK back to the client, and then afterwards just sends the data, right? Because it has some processing time or something else. I read about OSX server that might do that, and I also read that in particular cases, if it's not in the SYN ACK, the server will send the data immediately without waiting for the final ACK to come back from the client for the three-way handshake. So there's some variation in implementations of this feature.
Can you show us the packet 1 and 2?
Sure. So yeah, I think I would have done this anyway, but just do this right now. So if you open up, I think I need to increase the slide a little bit. Is that still okay for you to read in the back? Okay. So let's look in the TCP header of that first SYN and open up the options field. And this is the option that you would normally not see in a regular SYN. It's requesting the fast open cookie. And then in that SYN ACK packet, we should see, oh yeah, the server does support fast open and offered me a cookie. Right? So if we now check out the next SYN, so the next connection to the server, we see that, yep, there's a fast open cookie included in the SYN, right?
Because it's the length plus 64 bits.
Sorry, the length of the cookie is 64 bits. Yeah.
Yes, and then plus the length, that's why it's 10.
This is the length of the field, right? Correct. Yeah. Okay. Let's do this again. Right. One thing I just missed out, and we did this already. There is some kind of denial of service connection, prevention included in the SYN cookie, because as you might imagine, if now every server would support TCP Fast Open, I could shoot thousands of SYN to that server, including a cookie maybe, and make him reserve all the resources for answering these connections, right? So that would be a perfect denial of service scenario, and pretty easy for me because I just need to send SYNs, right? Just fire SYNs at him. But I need to include a valid cookie, otherwise the server is not reacting on this request, right? So even if I have a server that supports Fast Open, but I include a wrong cookie in my SYN, the server is not going to answer it, or at least not reserving any resources at his side. All right. Yeah, we rechecked on that capture already, so let's carry on. Well, with any new feature, obviously there's going to be drawbacks and challenges. The best worst case scenario, and this comes back to the question asked earlier, what if this connection is getting refused because there's a firewall somewhere along in the path that is not supporting Fast Open or doesn't even know about it and considers the SYN to be non-valid, so it just drops it. What will happen is that the client runs into this retransmission timeout, which can vary based on the operating system, and then it resends another SYN without Fast Open option, right? So there's some sort of fallback mechanism included. Another possibility is that the data in that SYN packet is just getting stripped, so the server won't receive it. Could happen. And then there's a third possibility that is actually even worse, and I will explain that to you on the next slide. So let's just imagine the client is sending a SYN including data, and we're having a sequence number of 0, yeah, relative sequence number of very first connection, and we are sending 100 bytes of data, including the TCP Fast Open cookie. So what should be the SYN ACK and what should be the ACK number from that server coming back to the client? And if you have been to Chris Greer's classes or any of the TCP classes before, you know that the acknowledgement number is basically the amount of data I send to the server, right, plus one byte in addition. So in this case, we would see a SYN ACK with an acknowledgement number of 101. But let's assume that this poor little firewall here in the way is not aware of TCP Fast Open, and it sees an acknowledgement with a number higher than it expected, right? So it should be just 1 in this case. It's going to drop it, maybe. And the problem is that the client doesn't see that, right? And the server doesn't see that either. He received a connection request from outside of the network and is answering it and believes, yeah, that should work because I got the request in, but it's not. And then maybe after a retransmission timeout, he resends the SYN ACK and resends the SYN ACK, but the client never receives it at this point. So that could end up in a never-ending story, basically, at some point just resetting the connections from one of the other ends, and then maybe trying without Fast Open next time.
What you're really getting is one of the overall design goals of TCP was that the devices on the network were dumb, that all the intelligence would be in the endpoints. Therefore, if you want to do a new protocol, you have to upgrade your endpoints, but not the intervening infrastructure.
Yes, and if we look at those features like TCP Fast Open, we need to make sure that our intermediate devices are at least aware of it and handle it in a way that we can react on it at least, right? Yeah. Okay, so my references for you, a few things that I covered during this few slides are actually from a talk from whatever now happened, sorry. With the beamer or is it me? From a talk from a guy named Christoph Pasch. He's from Apple, and he has had this talk recorded on YouTube as well. So if you want to look up more details on Fast Open, I can just recommend his talk here. Also, the other two references, the RFC, obviously, underneath. So any more questions regarding Fast Open so far? If not, just throw them at me during the other slides. All right, but the actual talk is about how TCP evolved over time and how we can keep up with the bandwidth that we got in our physics today. Fast Open is just a very, very, very tiny part of it. So let's just wrap up what is actually limiting our throughput in the networks. And there are various things that we need to look into. We have performance of senders, obviously the performance of the receivers on the other side, and we have the performance of the network. So, I mean, we do have 10, 40, 100 gigabit networks in our data centers nowadays. That should be fine. But then when talking about not maybe local area networks, but the wide area networks, we do have an issue with some of the things that are going on there. And TCP, one of the TCP features is the congestion control mechanisms that TCP brings along. And this is something we're going to talk about in the next couple of minutes. So when looking at this picture and considering TCP and data transfer, how would you describe this? What kind of data transfer is this? Assuming we have a server at the end of that tunnel in, I believe, Hong Kong, this picture is taken from, and a client on this side. Do we see, what do we see? Is it
Brake lights.
Yeah, we see a lot of brake lights. That's a good. Luckily, the packets cannot break themselves. Yeah, so that would be interesting. What about the direction of the traffic flow? Sorry?
Outbound.
Yeah, could be outbound. Depends on the direction you're looking at. Yeah, but it's just one. It's unidirectional, right? So we have a lot of things going into that direction, with just a few cars coming back, a few packets coming back. And that's a perfect example for data transfer, right? So we have a client requesting data, and all of a sudden, everything rushes back at him, right? And also, there's, I mean, smaller cars, bigger cars, we have buses, trucks. So that is a perfect example how we can imagine a wire must look like when there's a data transfer. So going back in time, not too far, but one of the first TCP algorithms, congestion algorithms that have been there is TCP Tahoe. TCP Tahoe has been, I think, invented or at least been supported with BSD version 4.3, if I'm not mistaken, so that is quite some time ago. And it had already some good components that I was still relying on today. So what we see is TCP slow start. I believe everybody must have heard about slow start. If not, look at the retrospective page afterwards and see the other good talks from Chris Greer and Jasper and so on. Then there's another thing that you might or might not have heard about, AIMD. Does that ring a bell for anybody? Yeah? Okay. And fast retransmits. We all know about fast retransmits, right? Right after that, TCP Reno came into play. And TCP Reno included all those components, plus we are seeing fast recovery. Does anybody know what fast recovery means? Megumi?
Maybe 3 times because of thing.
Yeah.
It determines it's
Yeah. It does consider TCP, duplicate X. So we will see that on a later slide. And how we recover after packet loss. And then TCP New Reno came into play. And TCP New Reno is, I would say, still in use in quite a few operating systems. So if you were using, I think Windows XP had New Reno enabled. Maybe not in the first instance, but at least in SP2. And New Reno brought a new feature called partial acknowledgement. And then there's another one that I would like to mention, which is not a complete new algorithm, but it has an own RFC, so it kind of deserves to be on this list here. This is selective acknowledgement. All right, so let's see how the first component slow start works. So when talking about TCP and data transfer, we always have two parts, the sender and the receiver. So how many windows are you aware of in terms of TCP? What do we have? Like if I want to send a bunch of data to my receiver, can I just do this without any limits, or are there limiting factors? Sorry? The receive window, obviously, yeah, that's on the receiving side. can we see the value of received windows? Yes, we do. So because the receiver does report back the actual size of the received window when talking to me in TCP. What about the other side? What about the sender? Do we have a... Yes, so obviously in the TCP header you will see the received window of the other side, but since I'm only transferring data unidirectional, it doesn't really matter. So how does the sender limit his data flow? With the congestion window, correct. So on the sending side we have the congestion window, and on the receiving side we have the received window. And the congestion window is something that you cannot measure in terms of there's no value in the TCP header where you can look at it. And in most operating systems, and I didn't find a way to do it, you cannot even see it if you have access to the physical device. So you cannot see what is the current size of the congestion window. But how does it build up? So what we see here is the congestion window size, very easy in small steps. And on the x-axis we have the time. So let's assume our data transfer starts. The first thing that we have is an initial congestion window size. And this initial window size depends on the operating system. Some of them have 2 times the maximum segment size, some of them have 4 times, 6, or even 10 times nowadays. So just for this example, let's assume we start with 1 times of the maximum segment size, so 1 full packet. What it does then, upon the receipt of the acknowledgement from the server that is saying basically, yeah, I got your data, we are doubling the congestion window. So in the next round trip, we are sending 2 times full packets, so 2 times full MSS. And that continues on, and doubles with every round trip or with every acknowledgement that I get back to my packets. So we see a pretty fast ramp up of throughput in this case. So how long does this carry on? What does us stop or limit at some point? Can we just go forever and send data and data, or is there a limiting factor? Packet loss, correct? So let's just assume at this point here we are having packet loss. So a single packet gets dropped, or we are receiving duplicate acknowledgements or whatsoever. Then the sending side sets a threshold for his own reference, and this is called the slow start threshold, right? So after this, we are entering a new mode of increasing bandwidth, of throughput, which is called congestion avoidance. And this is the actual second thing that I had on my slide before, the AIMD. Is called congestion avoidance. So what happens now, on each acknowledgement that I receive back, I'm just adding 1 full MSS to my congestion window. And that ends up in a linear growth of my congestion window, right? Any questions to this so far? Sure. Yeah, so it doesn't get too large in terms of you are always lower than, or at least we can only max out up to the level of the receive window on the other side, right? So I cannot send more data than my receiver can actually pick up and shoot up to the application, right? Yeah. So
you mentioned the congestion window maxes out when you start getting data loss. Why would you have data loss just because the buffer size is larger on the server?
well, there could be a limiting factor as simple as I just have a 10 megabit line between my client and my server. So when I hit the 10 megabit, at some point there will be packet loss because the switches or routers do not have buffer forever, right?
I thought congestion was the size of the buffer on the sender side, nothing to do with how fast the data is being sent.
Well, if you consider that the congestion window, after I shut out all my data that I have in my congestion window, I'm waiting for an acknowledgement from the other side, right? So I cannot send any more data if it's not getting acknowledged. In that case, if I can shoot more data in one bucket to that receiver, obviously I will have a higher throughput in the end, instead of just waiting for every...
Congestion was the size of the buffer on the sender side.
Right.
It has nothing to do with how fast you can get the data out of that buffer and across the wire to the other side.
The congestion window is how many packets or data I can send in one go, in one round trip, after waiting, right? So if I can send more at once, obviously there's more throughput, right? Okay. So one thing to notice, slow start, yeah, it's actually not really slow. It makes us ramping up the throughput pretty fast until a certain level, and then we change modes, right? Then we change into congestion avoidance. Just to keep that in mind. So, TCP Reno. What happens if we experience packet loss? So one thing that I can tell there's packet loss is, obviously, if I run into a timeout. So I'm sending a packet, and I do not receive any acknowledge on that. How long do I wait until I retransmit that packet?
Differs by operating system? Some timer?
Yes.
200 milliseconds?
Well, the correct answer could have been it depends, right? As always. It depends on the operating system, but the actual value is the retransmission timeout. But you can look it up. In Windows, you can look up what is the retransmission timeout. I will show that later, how you can do that. So let's assume we had a congestion window of 12 times MSS, and then all of a sudden we hit packet loss, retransmission timeout. So what TCP Reno does in this case, it reduces the congestion window back to 1 times MSS. So you're back to the very basics again, to a very low level. And then, after that, I go into the slow start process again until I hit the new slow start threshold. And this value now, as you can see, is also lower as it has been before, because if you run into a timeout, which is the worst case of packet loss, basically, in terms of throughput, the new slow start threshold will be half of the congestion window before. So if I had 12 before, the new threshold will be 6, and after I reach 6, I will go into congestion avoidance and a linear growth, slow linear growth of my throughput. Okay? Does that make sense? So what is the second criteria how I can tell there's packet loss? Is there anything I can react on? And I've heard it before somewhere in the audience. On the one hand, I have a timeout, but duplicate ACKS, correct? So the receiver can actually see or tell me, hey, I received your data, but in between something is missing, so I'm sending you duplicate ACKS to let you know I'm still missing a piece of your data, right? In that case, things are not as worse as in the timeout example, because the actual congestion window will only decrease up to the new slow start threshold, which is the same, by the way. It's also half of the old congestion window. But I do not go all the way back to 1 and then have to ramp up again, and that will save us time, right? So this process here is actually called fast recovery and was one of the features that I showed you on the overview slide, right? All right, any questions to this? Okay. So, next up, New Reno. And New Reno brought a new feature called partial ACK. How does this work? So let's just imagine I have a sender and I'm sending a bunch of data to my receiver. And I do experience packet loss in between, right? So I'm sending data, and of course you have to consider that when I'm sending data from this side and I do have a little bit of latency on this line, the time goes down here on this axis, on my y-axis. When I'm sending data and I'm currently at this position here and the receiver already sent back the acknowledgements, I haven't received them yet because I'm only just here in time, right? So even then I'm sending more data, I haven't received any acknowledgements yet. The receiver is sending a next acknowledgement for the first data packet. I'm sending more data, I'm still not receiving any acknowledgements yet. And then after my 4th or 5th packet, I suddenly receive or start receiving the acknowledgements from the other side. Okay? So I'm here in time, I'm here in time. Now I'm receiving the second acknowledgement. The receiver on the other side is still missing data, is sending the third duplicate acknowledgement. And what happens now? I've already disclosed it. Fast retransmit, right? So upon receive of the third duplicate acknowledgement, or the fourth duplicate in sum, I should send out a fast retransmit, so a fast retransmit of the missing data. In this case, should be the data packet 1, because that's the one he's requesting for, right? The receiver only acknowledged 0, but it didn't acknowledge packet number 1 yet. So what I do is I send out data number 1. So what should happen now? Because we have additional packet loss here in between, right? So data packet 3 is also missing. What should happen now? What acknowledgement should the receiver send back to me at this point in time? Acknowledgement number 2, obviously, because it's still missing packet number 3. So it cannot acknowledge all the data because there's still something missing in between. So it sends back acknowledgement number 2. So following this methodology, the next thing that should happen is sending a second ACK, a third ACK, and a fourth ACK, and then, only then, I'm resending the missing data number 3, right? But with partial acknowledgement, you would actually see that it's immediately resending the packet number 3 instead of waiting for more duplicate acknowledgements to come in, right?
Why don't we send number 2?
Sorry?
No, we have to, okay, fine.
Oh, good? Okay. Right, so if there has been packet loss in this stream before and we have received duplicate acknowledgements, then for the next fast retransmit, I'm retransmitting immediately after I receive the next acknowledgement. I'm not waiting for any further duplicate acknowledgements, yes.
So we didn't receive an acknowledgement for number 2. We got 0 3 times, but we didn't get an acknowledgement for number 2.
We saw it, yeah, sorry. I was running out of space, so I kind of had to shrink everything a little bit together. So this is the acknowledgement for 2, and then obviously the next should be. Is that clear? Any questions? Yes.
So is this the acknowledgement the 5?
The next acknowledgement, you mean?
Right.
Yeah, the next could be 5, yeah, obviously, because it has already received all the data, right? And I haven't sent any more in between. So yes.
How does this compare with you with that? Because in TCP, you don't have to necessarily get an app for every single packet you send out.
You don't have to, but at least you need to have an acknowledgement for all the data you have sent out, right? So depending on the operating system, you either receive an acknowledgement on every packet or on every 2 full MSS packets. Depends whether it's a Linux or a Windows system, right?
Yeah, but how do you, the point is that the second packet you send out there says, I received data 1 as well. Otherwise, I wouldn't have been sending you an app.
You mean this act?
No. The very first X.
Yes.
Okay. You receive it or receive it, but it did receive the next one. It should not be sending an app. At that point, you should say, wait a minute, I got out of sequence packet.
Yes, if you could only send the acknowledgement once, I would be waiting forever because I don't hear anything back from my receiver, right? So the RFC says that if you receive more and more data, even if there's something missing in between, you should acknowledge or must acknowledge this data with the number, the acknowledgement number of the missing, only received packet in this case, right? So you only receive data 0, so you need to continue acknowledging data 0, because then on the other side the sender knows, okay, there's something missing in between, I need to resend 1.
Yeah, the spec says that by acknowledging data 2, then you're saying, I also got data 1.
Yes, but there hasn't been any acknowledgement for 2 yet. Right? At this point in time, it's only acknowledging 00000. After I reset data 1, I receive an ACK for 2. Because that's the next thing. Data it received. If this packet loss would not occur, then after the fast retransmit, you can actually acknowledge all the data, so data 5, at this stage of time. Right? But it couldn't because there's still something missing in between. With selective acknowledgements, though, which I didn't have on the slide, you would see that there's more options in the acknowledgement saying, okay, I received data from here to there, then I have something missing, and I received data from here to there, right? So that's another thing that came afterwards. By the way, did the microphone turn off, or do you still hear me in the back? No? I mean, I do have another battery. I should try to change it. In between. Battery low. Okay, that explains it. Any more questions regarding this?
How does it know that reset data point? Is it just go reset the one with the next sequence?
How it knows to reset data tree?
Yeah, because they knew that it had reset.
Test? Oh, that's better. Yes, because the acknowledgement number in this case that it received was acknowledgement 2. So the receiver said, okay, I received everything from you up to here. So the sender then knows, okay, obviously the next thing I need to repeat or fast retransmit is data number 3. No, at this point not. Well, it depends. I mean, I think correct me, Stark, if I'm wrong, a few implementations of operating systems resend all the bunch of data they have sent in the same congestion window before, instead of just resending one packet. But yeah. But nowadays you will see selective acknowledgements, so it won't look like this anymore. That's this kind of history, right? What you might see it with older or smaller devices, IoT devices, might be the case. Okay. All right. So, having seen this, a few questions to you. Can we solve all the congestion problems with more bandwidth? What happens if we see something like this, which I call a large fat pipe, and maybe we also have some high latency in there? Imagine there's a 10 gigabit per second link across the Atlantic from Germany back to the East Coast. Can we actually work with algorithms like New Reno back in the days to fully max out that bandwidth that we have there? The answer is kind of no, and I'll show you why. So let's look at this pipe. In this example, we do have actually a 10 gigabit pipe, and we do see a latency of 100 milliseconds. So that is basically from Germany to East Coast USA. The value, the actual congestion window and receive window we would need to have to fill out this pipe is 120 megabytes in size. So that means I need to shoot 120 megabytes at you in one go without waiting for any acknowledgements. And the receiver actually needs to pick it up, acknowledge it, and ramp it up to the application in one round trip, basically. So the problem with that is, I mean, aside from the fact that this is quite a large window, and if something goes wrong there, we do have a problem, right? The problem here is that with TCP Reno or New Reno, the first ramp up, which would be the slow start, is pretty fast compared to what happens next. But then, when we reach out the maximum bandwidth and we encounter packet loss, in best case, our congestion window goes down to half of the bandwidth before, which means we are back to 5 gigabits per second. But since we are immediately going into congestion avoidance after that, so the linear growth of the bandwidth, right? The time it would take to ramp up to 10 gigabit again would roughly be 1 hour with TCP Reno. So that can give you a clue about if that's efficient for nowadays networks, right? And this would happen all over the place again. So Microsoft actually came up with a solution to this with Microsoft Vista, Windows Vista, and Server 2008 in, I think, at least release 2. They introduced a new congestion control algorithm called compound TCP. And compound TCP, as the name might indicate, combines two things, or two variants of the window. First, we have a loss-based window, like we have seen before with the congestion the congestion avoidance, so the AMD algorithm. But then in addition to that, we also have a delay-based window. So that means that the sender is continuously monitoring my delay on the line or in this particular connection and adjust the congestion window according to that, right? So there's some sort of algorithm behind that. I can't explain you here, but because I didn't even understand it my own, because there's like a 20 slides or 20 pages of RFC document on that. But we just need to take it for granted now. Sure. Congestion window, yes. So the principle of compound TCP is actually these three things, and those are the things that it should address. What we need is efficiency, we need fairness in terms of round trip, and TCP fairness. Because imagine you're using this intercontinental link, maybe across the ocean or over the ocean, and there's not only your session on that link, there's multiple TCP connections on that link, and you will experience packet loss through all of them, right? So we need to make sure that if we have multiple connections going one and the same path, that we kind of be kind to each other and nice, and allow the others to use the same bandwidth or at least level it out at some point, right? We don't want to be rude, obviously. So next up, and then we are getting pretty close to the next demos. With Windows 10, there's even been a new congestion control algorithm called cubic TCP. Cubic TCP is the one congestion control algorithm that really addresses the high latency networks, right? So everything bigger than 100 milliseconds, cubic TCP is probably the one algorithm you want to use for. It makes sure that it grows the congestion window pretty fast, pretty aggressive. But then on the other hand, it's also kind of fair to other sessions on the same line, right? So if you open up your Wireshark and you have captured a a session that was using cubic TCP, you will most likely see a pattern in the I/O graph looking like this with this convex and concave shape. That is an indicator for cubic TCP, right? So what you will see is basically this sawtooth kind of pattern with just round edges. Another thing that they changed in Windows 10 is the initial window size, so the initial congestion window size. Remember what I told you in the first couple of slides. There's an initial size of 1, 2, 4, or 10 maybe, and with Windows 10 and Server 2016, they increased it to 10 times the maximum segment size. All right. One more thing I would like to show you, but you probably already know. Of course, we cannot only look at the sender side, but we also need to care about the receiver side. And there, as already mentioned earlier, we have the receive window on the other side of that communication. So the receive window is kind of interesting because in former times you had a static value. Not static value of the actual size, but there was a limit of 65K of receive window, right? Because that's the length of the TCP option. You cannot go beyond that. So something that was introduced is called TCP window scaling. And what does this do? Basically, it allows a window of up to 1 gigabyte in size by using a multiplicator for the actual size. So the 65K value can be multiplied with a particular value. And if you open up your Wireshark and you look at the TCP window scaling option, you will see that there is a shift count mentioned in this. And I think actually during the Packet Palooza yesterday, there has been a question, what is the actual value of the TCP window size scaling factor of 8? Yeah, probably. So people who were in my class yesterday, or in my talk, they might have known that the answer is 265. So you need to multiply the value of the actual window size by 265 if you have a shift count of 8, and then you get your actual window size. Wireshark does that for you, so you don't have to do that. You will see it further down in this. This is a SYN ACK probably. you will see that there's a value in brackets that actually is a calculation based on Wireshark and what you see in the window size and scaling factor. So you don't have to do the math by yourself. The problem is that this is cool if you have one of these large fat networks, because then you can say, okay, I have 100 milliseconds, 1 gigabit or 10 gigabit of throughput or of bandwidth. I can calculate the perfect window size for it to max it out as good as possible. But in modern networks, you will not only see the same latency, right? It depends on the utilization of the line, everything else. So if you have a variation of latency, this is not really good. So another thing, yes.
So on 1 byte. So the value is 8. It could be all the way to 255.
The value, the maximum shift count could be 14, and 14 would give you, in the end, I think 1 gigabyte in size. Yeah. So another thing that has been introduced is the so-called receive window auto-tuning. So what it does, a mandatory thing is that you have window scaling enabled, right? There's no way around it, so you need to have window scaling. And then it also measures the bandwidth delay product, BDP, continuously, and calculates based on that if I could increase my window size to a certain point. So, and this happens per connection on your host. So if you have multiple connections to multiple servers, you will have different window sizes and different values of receive window auto-tuning enabled. So I'm going to show you this in one of the traces. But for that, just take a look at this topology real quick. So this is the lab setup that I was using for taking all the traces that you might have downloaded already, or the traces that you could download afterwards. So I built up a little Hyper-V-based machine, and I installed in total 4 virtual machines. One is the FreeBSD router here, which I use DummyNet on to simulate WAN pipes and latency. And then I have 2 virtual switches, and one of them connects a sending side, so the VM04 will be my sending side. And then on the other side, I have 2 different hosts. One of them is a Windows 10 machine, and one of them is a Windows 2016 server machine. And the reason for that, I will show you later on. So we have 50 megabits of total bandwidth, and we do have a latency of 100 milliseconds, right? So this machine here is just used for capturing the packets. So what I did, I installed a Wireshark on this virtual machine, and I don't know if you're aware of this, but with Hyper-V, by default, even on your workstation, you can enable virtual port mirroring, so virtual span port. Has anybody used this before? No? So if you go into the Hyper-V server and check out the advanced networks settings for these particular VMs, you can enable a port mirror and have to define if this is the source or if this is the actual destination of my traffic that I want to see. So I did that for, I think, actually this interface here, so I can capture everything that's going across the WAN links. Okay. So let's look at this in the captures. So I'm connected via VPN to my machine at home. That is running the Hyper-V, and if I type my password correctly, you'll probably see something. Third time is the lucky one. There you go. So what you see here is basically the setup I just showed to you. I have a green machine here with a green background. This is my sending side, which was on the left-hand side of the topology. And then on the other side, I have 2 virtual machines. Both are behind the second V-switch with the red background. The only difference is that I think this one is the Windows 10 machine. Let me verify for you quick. Yeah, so we got the Windows 10 machine here, and below will be the Windows Server. So one pretty cool tool I used during my research is this so-called NT-TCP. It's just a little program that you can download for free from Microsoft. And you can use it to test performance in the network. And it gives you a couple of options. So you can define how many sessions will I see, on which IP address should I listen, what size of sending and receive buffer do I have. So this gives you some nice options to play around with. And it also includes a pretty good documentation where you can read about all the options that you have. So I can just encourage you to use it for your own testings. So, sorry. Is anybody aware of the get net TCP commands in Windows PowerShell? Okay, that's good. So with Windows PowerShell, you get a few things that you can look up if you're actually curious about what's going on. So the get net TCP connection command, for example, is the equivalent to a netstat on Linux or on Windows even. So what you can do is you can show or can see what are the current established connections. One interesting detail here is that my screen is not large enough. Let me see if I can increase this. At the very right end of this table, you will see applied templates, right? So there's a column that says there's a template for something, and I will show you why this is later on. What you can also do is use a netstat-y, which is a little bit easier to use because then you have just to reload. Oh yes, sure. Still, thought it would be. There you go. So netstat-y gives you a more clear overview about what's going on. So let me open up or fire up this NTTCP command or tool to just have a TCP connection between my two hosts. So in the first instance, I'm going to use my Windows 10 machine on the receiving side. So what I do here is basically, and I hope you can read this. I'm saying, okay, start NTTCP with the -r as a receiver, -v for a little bit more output, and then I'm going to have one TCP connection, and the asterisk means balanced across all my CPU cores. If you have more than one core, you can balance the actual load. Listening on this IP address, and I want to have a receive buffer of 10 kilobytes, right? So you just start this. Bring up the throughput graph here. And then, sorry, I'm doing the same thing basically on the other side, but this is the -s for the sender, obviously, and I'm going to connect to the 23. So that should give us a certain amount of throughput on that line. So what we see is about 800, 850 kilobytes, 830 maybe. Which is not much because, I mean, we do have 50 megabytes in total, right? So we could use some more bandwidth. Let's see what we can do about that. So let me just stop this here at this point and increase the sending buffer to 100 kilobyte and the receive buffer on the other end. And I'm just playing around with the application, right? So this is not TCP, that's application buffer. Also to 100 kilobyte. So let's see what happens now. I need to restart this. There you go. What do we see? Is that tenth the time of bandwidth that we have seen before by accident? No, it's not, because it all depends on how fast TCP gets the data or how much amount of data from the application, right? So following that principle, what should we see if we increase it or multiply it by 10 again? How much throughput do you expect to see on the line? Any ideas? Right, if not, we just start it. So following that principle, and we had 8 point something megabit before, we should, in theory, see that this maxes out the 50 megabits of bandwidth, right? Which it does at some point. And as soon as Windows Task Manager scales, we can see, yeah, we are pretty much at the limit of my physical bandwidth. So we cannot go any further. We see a few ditches here and there, but this is due to congestion control algorithm. Okay? So just memorize how this graph actually builds up, all the throughput builds up. And then I'm going to do the same thing on my other machine here. Open up the task manager as well. And I use straight away 1,000 kilobytes as receive buffer and 1,000 kilobytes of send buffer, but now I'm connecting to the machine 22. And let's just compare the two throughput patterns. What you can see immediately, the time it takes to ramp up the bandwidth is a little bit longer as before, right? And as soon as the task manager scales the view, it should happen right now. Does that look similar to the other throughput we have seen in the Windows 10 machine? Is there a difference? Do you see anything different? Or does it look the same? It's the same pattern. Right. So if you compare this, or in terms of TCP throughput, we can say this is a linear growth, almost like congestion avoidance all the way, right? So we see there's, before it disappears, there's a peak at the very beginning, and then maybe some loss, and then we are hitting congestion avoidance. And it takes some time for it to go back up to the actual maximum bandwidth. And even after the second time we see a loss, it also takes some time to ramp up again. So why does it do that? I mean, I have a Windows 10 machine and a Windows 2016 server machine. They both should be using the same TCP, right? As I mentioned before on the slides, might be compound TCP, might be cubic. So let's look at what's going on. What I will do here, I will restart the session again, but then using the netstart command to actually see what's going on. So as soon as data flows, which it should right now, I'm going to switch to the other PowerShell here and redo the netstart-y. So what we can see now, and this is my session I'm currently looking at, it applied a template called Internet Custom. The other session here that I see, the HTTPS session, there's a template called Internet. So it seems to be a difference. So with Windows PowerShell, with Microsoft PowerShell, you could also look into the actual settings of the TCP. And you can do that by issuing the get net TCP settings command. And when you do that, and I will just include a -more, it will provide you a list of templates that Windows is using on different connections. So for example, we are seeing an automatic template with no proper values, but we're seeing an internet custom template. And we are seeing a data center custom template and something more and more, and there's an internet template. So let's compare these two. I was seeing some connection going on using the internet template. So what you see here is that the congestion provider is CTCP, which is compound TCP. That should be the default in Windows 10 and 2016, correct? You can also see what is your RTO, your retransmission timeout. So as you mentioned before, it depends on the actual OS. How long do I need to wait upon a timeout to resend my data? In this case, it would be just 300 milliseconds, right? But then we also have seen traffic using the internet custom template. Oh, sorry. And there's a difference, right? Here it says congestion provider is default. Now what is default? The answer you can always use for that is, it depends, correct? So as per documentation of Microsoft, default congestion provider for a Windows 10 client is TCP New Reno. And compound TCP. And for a server 2016, it's data center TCP. Now, what's data center TCP, you might ask? It's actually quite simple. Data center TCP means I have a new Reno congestion control algorithm with ECN on top, explicit congestion notification. You might have seen that when you open up the Wireshark in one of your data centers or local area networks, captured a few things. In the SYN and SYNAC, you will see an option called ECN. This option is used by either hosts or routers or switches in between that are aware of it to let one or the other know if there's congestion or future congestion going to happen if this continues to transfer, right? But basically, data center TCP is a new Reno stack with ECN on top. So, and I must admit I tricked you a little bit because I've defined a so-called net transport filter before this class on this machine, which matches this IP address, which is going to be which is my 2016 server machine, and it should apply or use the internet custom template instead of the default, which would be compound TCP. So I'm forcing it to use an old congestion control algorithm instead of using the default one. And that's why you see this difference in the throughput. And to even illustrate this even more, I will show you a trace that is also included in the demo file that has both kind of sessions in it, and we can compare the actual throughput in the same capture file. So if you open up, or if you want to follow along, if you open up the demo 03 New Reno versus compound TCP file, you will see, if you look at the conversations, that there are two sessions in it. It's a little bit small. The one session is using TCP port number 5002. The other one is using 5003. So if I open the I/O graph, and I've created two lines here. One is for one has a display filter filtering on just the 5002 session, and the other one on 5003. You will see the actual throughput of both sessions, and make an educated guess which of these sessions is the compound and which is the new Reno. Anyone? The bottom one is? Yeah, that's correct. So the green one, the top one, is the compound TCP, and the red one is the new Reno. Just two sessions in a lab scenario on the same wire, on the same machine, same sender, same receiver, just different congestion control algorithms, and you can see immediately what difference you have in terms of reacting on loss and how fast the actual congestion window ramps up again, right? So with compound TCP, we see that even here we're pretty close to the maximum of throughput that we can get, whereas the new Reno, can't keep up anymore. So this is a nice reference file if you want to compare those. You should also be able to see this kind of pattern if you follow along in the TCP stream graph, or just go through the packets one by one. Another interesting file is in that zip file is called receive window auto tuning, and that's maybe the last one I will be able to show you. And if you have been to the Packet Doctors session yesterday, Sake was actually using the TCP stream graph to analyze one of the issues that one of the guys in the audience had. So I will do this right away here as well, just to, because we are not troubleshooting an issue. I will just show you, or want to show you, how the actual receive window auto tuning works, or looks like in this case. So there's just one session in there. And if you open up the TCP stream graph, and I will just zoom in to this point in time real quick, you will see this kind of pattern. So the blue little dots here are our packets, data packets coming in, and you will see the sequence numbers on the y-axis and the time on the x-axis. And what is the green line? Does anybody know? the receive window, correct? So this is the receive window that my receiver announces back to me and says, okay, you can send me more data, I have space for you, just follow along. And at some point in time, it looks like there's been a large increase of receive window. And this is what receive window auto-tuning does. You can see this even better on, let's see, on a later point in time, or at a later point in time, here. So for any reason, the receiver decided at this point in time that, okay, based on delay, based on loss, based on whatever reason, or whatever indicator, I can increase my receive window. So please go ahead, send me more data. The sender in this particular case, yeah, doesn't care. I mean, he just sends in a constant rate, nothing fancy. But it could, in theory, increase the sending rate and increase the congestion window up to the receive window of this receiver. So if you see this kind of pattern in any future traces, you at least have a clue what this might be, right? Any questions to this so far? Yes, please. Yes, the slide deck will be available after SharkFest, as soon as Angelo managed to sort all the things, and then it should be uploaded a few weeks after, a few days after. And I will also include the slide with the reference to my demo files, so you can download it if you like to. Further questions? Yes, please.
You talked about a lot about Windows stacks. Mm-hmm. What about Linux?
Yeah, I knew this question was going to ask. So I was asking the same question when I was preparing this talk for SharkFest EU, and I decided to just concentrate on One OS first, because otherwise I wouldn't even finish this this talk until today. Yeah, there will be a similar behavior. So cubic TCP is available for Linux as well. Compound TCP is available for Linux as well. And again, it depends on which kind of Linux you're using.
Next year.
Yeah, right. I will have the same talk next year just with Linux instead of Windows. Yeah. Okay. I think that pretty much brings me to the end of my session. So first of all, thank you for being here, and more important, please use the app. I know you're kind of tired of it already, but yeah, this provides me some feedback after the session, what I could do better, what might be an interesting topic for you. So if you use it, provide me some feedback, that would be much appreciated. Thank you.